welcome to this very important public lecture at the University of Melbourne. My name is James Angus and I'm the Dean of the Faculty of Medicine, Dentistry and Health Sciences. It's a great pleasure to welcome you to tonight's R. Douglas Wright lecture. I'd particularly like to acknowledge the presence here tonight of Professor Glyn Davis, our Vice-Chancellor. The University also acknowledges the traditional owners of the land on which our campuses are situated. We pay our respects to their elders, both past and present, and extend that respect to all Aboriginal and Torres Strait Islander Australians who have made a contribution to the life of our university. The Friends of R.D. Wright, who sponsor this series of occasional lectures, are an independent, informal, ad hoc group, in fact a group of mates of R.D. Wright, who got together to do something to honour him while he was alive. Chief amongst these are Professor John Coghlan and Professor Bill Louis, down in the front here. And I'm delighted that they are here in spirit and very much alive in selecting the topic and lecturer of this wonderful memory for R. Douglas Wright. There is no endowment. Each lecture has been funded by sponsors, the Friends of R.D. Wright, the Faculty of Medicine, Dentistry and Health Sciences at the University, and Lady Wright. The continuing support from Lady Wright has been especially valuable to the Friends. The R.D. Wright lecture is not an annual lecture, but a series of occasional lectures, very dependent on who is available and when. The topics and lecturers are chosen to reflect Wright's wide academic interests and broad contribution to the university. Pansy Wright was often the epicentre of controversy, as have most of the previous lecturers. These lecturers are often people who have promoted valuable, useful new technologies, often also precipitating controversial discussion. They are chosen to create the opportunity for them to present their findings and point of view. They are usually people that have marched to a different drum or wish to cut the cloth of some subject in unconventional or very new manner. Let me now say a few words about tonight's distinguished lecturer. John Hugh Seiradakis was born in Chania, Crete. He obtained his degree in physics from the University of Athens, his Master of Science in 1973 and PhD in 1975, both undertaken at the Victoria University of Manchester. From 1975 to 1985, he worked as a postdoc researcher at the Max Planck Institute for Radio Astronomy in Bonn, Germany, at the University of Hamburg, and at the University of California, San Diego. In 1985, he was elected an associate professor at the Aristotle University of Thessaloniki in Greece, becoming a full professor in 1996, a position that he continues to hold. His major scientific interests in astronomy focus on neutron stars, pulsars, neutral hydrogen modelling in nearby galaxies, the centre of our galaxy, flare stars, the moon, and archaeoastronomy. In December 2005, the highest European Union prize, Descartes, was awarded to the Neutron Stars Research Network Pulse, in which he is one of the founding members. He served as a member, secretary or chairman of the Greek National Committee for Astronomy and secretary or president of the Hellenic Astronomical Society. He is a member of the Antikythera Mechanism research group. Since 2007, he has given more than 100 lectures, public or scientific, in Greece and around the world about the Antikythera mechanism. Since the device was brought up from the sea in 1900, from where it had lain for over 2,000 years, a legion of archaeologists, engineers, computer experts and astronomers has tackled the task of decoding what it was used for and what its capabilities were. Alan George Bromley, an associate professor at Sydney University and a computer historian in the 80s, made a useful contribution by making working models with colleagues at the British Museum. In each decade, technical advances made incremental steps in our understanding possible, and newly developed polynomial texture mapping has allowed new vital insights that were unbelievable just a few years ago. Archaeoastronomy and John Seiradakis are now in the focus at the cutting edge of these advances. I now invite Professor Seiradakis to present his R. Douglas Wright lecture entitled The Antikythera Mechanism, Astronomy and Technology in Ancient Greece. Please welcome our orator.
Well, thank you very much. I would like to say that I'm honored that the Vice-Chancellor, Professor Davis, is here. I know how busy you are. Thank you very much for inviting me. The Dean, Professor Angus. The first person that actually communicated with me in Greece was Professor Cogland. Thank you very much. I appreciate the many emails that we exchanged. And, of course, I should not forget Jan Powell, who organized, at least this is what I understand, this meeting together with some valuable colleagues. So thank you very much. Most of all, I would like to thank you, the audience. I hadn't expected to have such a large audience in faraway Melbourne. I say far away. For me, it's a very long distance. One of the flights was 13 and a half hours. But it was lovely. It was an enjoyable flight. It means that you are here. It means probably that you have heard something about the Antikythera mechanism, and you would like to learn more. I hope that after the end of this lecture, you will know much more about what was happening in those Hellenistic times, about astronomy, and about technology in ancient Greece, something which is unheard of. I mean, we knew the Greeks were good in poetry, in theaters, they were good in building statues, they're good in music, algebra, geometry, arts, but technology, that was very, very new. And it has disturbed the flow of knowledge about the evolution of technology, bringing back several steps back the initial steps that led to the technology of our recent times. I thought of putting a couple of slides to start with about astronomy in ancient Greece, because I'm going to say you a few things. You say, is it possible that they knew about it? So I have 3 slides that I will briefly describe how Aristarchus measured the distance of the sun in the 2nd century BC. Now, Aristarchus was a very fine scientist, and he had a very simple idea. If when the moon is on the quarter phase, this means that the sun, which is far, far, far away in this direction, illuminates half of the hemisphere of the moon, this hemisphere of the moon, and the other half is dark. We, from Earth, from down here, see half of it illuminated, and the other half is dark. This means that this angle should be a right angle. It's simple. Now, if the sun is at a very far, far, far away distance, very, very far away, then this angle should also be 90 degrees. Just imagine taking this thing and putting all the way up down to Sydney. Then these lines become parallel. So this line, if you could measure it, then on this line depends the distance of the sun. It was a very difficult measurement because he had to do it while the phase of the moon goes on the 1st quarter, and the sun is just about setting. So he had probably something to measure angles, maybe 2 diopters, and he was measuring this angle between the sun and the moon. This is this angle between the sun and the moon. And he found that this angle was 87 degrees. So if this angle is 87 degrees, it's very simple. All the maths were there to calculate that the distance of the sun, so this distance from the sun to the Earth, is 19 times the distance from the moon to the Earth. So simple. I mean, this is you can imagine that if the sun was very close at the distance of the moon, then it will be coming closer and closer and closer and closer, and this angle will be 0. This angle would be 0. On the other hand, as I said, if the sun is at the infinite distance, this angle should be 90 degrees. So the distance of the sun depends on this angle. Of course, we know, and if this is so, then the distance of the sun is 19 times the distance to the moon. Of course, we know now that the true distance is that this angle is 89.86 degrees, close to 90, but not exactly. And this distance is 400 times the distance of the moon. Okay, however, that was the first time that somebody calculated that the sun must be much, much further away than the moon. I mean, just think about it. It's a really new knowledge. Now, he was a man that had a lot of intuitive. He was very intuitive, and he knew something else. During eclipses, the moon just about covers the sun. This means that they have the same angular diameter. The diameter of the moon is exactly the same as the diameter of the sun. In fact, this is one of his drawings that have been found later, done by the Arabs, and then it came back to Greeks as well. Okay, so if this is the moon and this is the sun, and they have the same angular diameter, so this angle is the same for both objects, then if the sun is 19 times the distance of the moon, then his radius of the sun must be 19 times the radius of the moon. And I think this is now where the genius comes in. If you have two bodies rotating around each other, then the light and less massive body rotates and goes around the more massive one. And this is how Aristarchus, about 2,200 years ago, he discovered the heliocentric system. Everybody was believing that the Earth is the center of the universe, because every morning you see the sun rising from the east, setting in the west, the stars, the planets, the moon, all everywhere. It is logical to assume that the Earth is in the middle. Now, this idea of Aristarchus did not go through, I think, under the shadow of the great Aristotle, who couldn't believe that the good God could not put man on the center of his creation. So the knowledge was lost, except it was written down. Ptolemy transferred it to us through Almagest, and now we think that we know how he discovered this. And another thing that I would like to talk about, okay, well, say, yes, is that there is the way that Eratosthenes measured the circumference of the Earth. Just imagine, you sit here, and somebody tells you, I give you 50,000 Australian dollars. Could you measure the circumference of the Earth? What do you do? Now, Eratosthenes was the head of the Library of Alexandria. It was a very curious person. He would go to the flea market, and he would talk to people. And one day he heard that there's a very deep well in ancient Asii, so ancient Assini. This is where the Aswan Dam is now. That one day in the year, but every year, the sun is reflected on the water of the well. Now, of course, this is easy to understand what is happening. The sun is exactly perpendicular, exactly opposite, above the heads of the people in ancient Assini. So he asked around in Alexandria, saying, well, have you heard, do you have any such well here? And the answer is no. We never see the sun, never, even the deepest, we never see the sun reflected on the waters of wells here. If somebody will say, yes, we have another well, then this means that as the sun is very far away, it means that the two places, Alexandria, where he was living, and Assini, Sieni, were at the same level. So the Earth was flat. But this was not happening, so the Earth must be round. And he set up a little experiment. He put up a pole in Alexandria, and the day when the sun was reflected at the well in Sieni, he measured the shadow of the stick, and by measuring the shadow of the stick, he was able, this the shadow is here, he put a little wiggle here, he was able to measure this line. And this angle, I'm sorry, this angle here, the small angle here. But this angle is exactly the same as this angle. You can see that this line is continuous here, and this is parallel to this line. Simply geometry. If this angle is 7 degrees, this is also 7 degrees. Now 7 degrees is about 1/50th of 360 degrees, which is a full circle. So if this angle is a 50th of a full circle, then this distance from Syene to Alexandria must also be a 50th of the circumference of the Earth. Simple. So he got Vimatistes to measure this distance. He found that this distance was 5,000 stadia. So if you multiply this by 50, because to get the full circumference, this is 250 stadia. And if a stadium, which is 164 meters, then the circumference of the Earth is 41,000 kilometers, which is very close to what we know now. This is very close to the number that he came up, by about 1%. Okay, I gave these two examples, only these two examples. I will not go any further into ancient Greek astronomy, only to show you that their knowledge was very advanced. So let me now go into the Antikythera Mechanism. Oh, yes, well, we know that it was the odometer of Herons, but I'll maybe talk about it later. Let me now go into the main part of my talk, about the Antikythera Mechanism. And I will start with a very quick summary so that everybody, even if you're going to go, they know what the Antikythera Mechanism is. So it was a geared astronomical computer. It was really a computer with the full meaning of the word. A computer should have input, should make calculations, and should have output on a scientific scale or on scientific scales. For example, a planetarium is not considered to be a computer because it does not have its output on a scientific scale. It shows pictures. You cannot measure anything. But as you will see, the Antikythera Mechanism had all its output into scientific scales. In fact, the first ever discovered up to now anywhere in the world. Scientific scales with divisions, numbers showing exactly how to measure things. It would calculate the position of the sun and the moon very accurately. I mean, the position of the sun and the moon and the planets are all in one level, one surface. So if you want to calculate the position of the sun and the moon and the planets, you do not have to do it on a whole sphere. It's simple. You have to calculate it on a disk, not on a sphere. And this is the ecliptic. In fact, the word ecliptic has been found in the Antikythera Mechanism. So it could calculate the position of the moon and the sun so accurately that it would predict eclipses. When do eclipses happen? Eclipses happen when the three bodies, the sun, the moon, and the earth, they line up. If the earth is between the moon and the sun, its shadows prevents the solar light to illuminate the surface of the moon, and to have a lunar eclipse. On the other hand, if the moon goes between the earth and the sun, then it prevents in parts, only small parts of the surface of the earth, because the moon has much shorter shadow. It is much smaller than the earth. And we have a solar eclipse. By the way, Australia is very well placed for the next solar eclipse. It will happen on the 14th of November this year. I will be coming back then. We have already booked 2 villas in close to Port Douglas, and we are bringing about 300 pounds worth of equipment, spectrographs, telescopes. If you happen to be there, don't be surprised early in the morning that suddenly the sun will disappear, the moon will be in front of it. You're going to see a shine surrounding around the sun with a black moon in front of it, and you're going to see some of the planets, some of the stars, the brightest stars, and this is well into the day. A very a very important astronomical phenomenon. That, for example, yes, we measure several things. We are trying to measure we do the thermography of the atmosphere of the sun. We are trying to measure the temperature at 7 parts by using spectrographs. Another thing that the Antikythera mechanism would do is to say when the Olympic Games were going to take place. The Olympic Games were happening after the first full moon, after the summer solstice. The Antikythera mechanism could calculate all this, so it was probably through this machine that the dates of the Olympic Games were announced all over Greece, saying, stop the war, we are going to have the Olympic Games, send your best athletes to Olympia. It was a complicated machine. The result is that it had to have a user's manual. And we have discovered up to now, we have decoded about 3,000 letters inscribed on the bronze plates of the Antikythera mechanism, of course with the full words and sentences. We have found, I will show you some of these sentences in the near future. Okay, now let me go a little bit back to the history. It was about 2,000 years ago when a very large boat, a very large Roman boat, an olkas, probably about 50 meters long and about 25 to 30 meters wide, full of treasures, were going from the Aegean Sea, so from Eastern Mediterranean, to Rome, probably carrying either merchandise or most likely loot. It was during that time that the Romans had captured Greece, and they were trying to bring ornaments and fine arts from the Greek cities to Rome. And this boat was faced with a very bad weather, and eventually it did sink between the region of Peloponnese and Crete, next to a very small island called Antikythera. It is between Peloponnese and Crete, as you see. In fact, from there, it's about 30 miles from this island to Crete. A good swimmer could just about do it. The boat was loaded with works of art and other precious artifacts. Maybe it was very fortunate that it sank there, because later, about 2,000 years later, in 1900, in fact it was Tuesday before Easter in 1900, when two boats from Simi, now Simi is a small city, a small island opposite the Turkish coast, very close to Rhodes, this is where Simi is, that they had taken a boat. In fact, they had been hired by, of that time, a millionaire, to go to the shores of North Africa to collect sponges. They were sfungarades, sponge divers. They had faced another storm. They put anchor on the same island, and for some reason, we really do not know, Elias Lycopandis, a photograph of this man you can see there, we met his daughter-in-law at Rhodes 5 years ago. She gave us this photograph. He was a very sturdy, very strong man, and he dived there for some reason, maybe to test one of the new suits, maybe diver suits, maybe to show to a novice how to dive, or maybe because it was Tuesday before Easter, and in Greece they were fasting, he dived down to bring some calamari or some seafood which we can eat without having any bad remorses. Anyway, he dived, and 50 meters away from the shore and 50 meters down, he found a very big shipwreck. Please note that it was a very difficult and dangerous exercise. This is one of the suits that they were using at the time. I photographed it at Simi when we went there to pay our respect to some of the divers, the 1900 divers that had died during the excavation that follows immediately after. Please note that it's a very rocky country, and also it is deep water. So rocky country, and then have very steep bottom going 50 meters out, 50 meters down, so very steep bottom. They did some excavations, some old photographs, either from the Cousteau Encyclopedia or otherwise. Now look at this. This is a very old photograph with the findings of the Antikythera wreck in the courtyard of the National Archaeological Museum of Athens. Within the next 18 months, 2 major marine excavations were organized by the Archaeological Museum, probably the Archaeological Society of Athens at the time, and they had found quite a few things. So, for example, lots of marble statues. They found, all in all, 104 statues, either whole or sometimes broken parts, a head, maybe a foot, a leg, or something. So the boat was full of these artifacts. Please notice that the upper part is very clean. It has survived, obviously, 2,000 years in the water, but the bottom part is not. Now, this statue was wedged into sand, and this is how it survived. The upper part survived, and the bottom part did not survive so well. But now, is it possible to have sand in such a steep depth, bottom of the sea? The answer is no. Most likely, the sand was the ballast of the boat, and the statues were wedged into the ballast so they did not move and break during the bad weather. The philosopher of Antikythera, it really looks like a philosopher. They have not discovered who he really is, but it's very, very expressive statue. This is one of the nicest bronze items we have in the museums in Greece. This is the Antikythera youth. We do not know if he holds the Medusa head, and it's Perseus, or if it holds an apple, it's Paris. The archaeologists have not managed to discover his identity up to now. Very beautiful glassware and other artifacts, a nice bed, etc., were found there. And among the other things, some corroded, calcified pieces of stone with obvious green stuff on it that they thought it has something to do with bronze or copper. And they put it in a box. Later, it was discovered that these boxes, they held something peculiar. One of the biggest fragments had broken for some reason. Either an archaeologist was a bit careless, or most likely because from the water, from the deep water of the sea, it came to the dry atmosphere and it broke. And inside, gears were found. Gears and some letters. Now, the archaeologists had never heard of gears of that age. In fact, no one has heard up to now, anywhere in the world, of fine cut gears as the ones at the Antikythera Mechanism, because this is what these stones were. They published this in 1903. In fact, they asked a captain of the Navy who knew a little bit of astronomy to describe it. And Pericles Radiadis did a very good job. He described the Antikythera Mechanism. But the archaeologist was very interested, of course, on the epigraphies, because they could put a date on the mechanism. So the newspaper started writing articles, and these articles went all the way to the United States, where a British scientist, Derek the Solar Prize, was working at the University of Yale at the time, and he heard about gears from the Greeks from the Hellenistic times. Now, this was unheard of. This man was a very learned scholar. He was a mathematician, a physicist, and he was also a philosopher of sciences. For those that know, he had read all the proceedings of the Royal Society, and he had made statistics and worked on them. I mean, it's like saying that a shell from there to there, he was reading it, he managed to read it throughout his life. Now, he came with the first aeroplane to Athens. He went to the museum, and with the help of Charalambos Karakalos from the Democritos Center around Athens, he did the first X-rays, in fact it was gamma rays, soft gamma rays, of the Antikythera Mechanism. And inside this calcified material, these stones, he saw that there were lots of gears. He went back, he came to Greece again a couple of times, and he made some models. He made some models that we know now they were not absolutely correct, but at least we know that he discovered trains of gears that they were cooperating, working together, producing astronomical phenomena, like the position of the sun, the position of the moon, and things that I told you before. Not eclipses yet, and not Olympic Games yet. But he was going from school to school, from city to city, as one of his nephews told us, teaching how wonderful technology they had in ancient Greece. Models were made after his research, and some of them are now, for example, this model is in the University of, the Archaeological Museum of Athens. This model is at the Technical Museum of Thessaloniki, both in Greece. And please notice that the back side of these both models, they have homocentric circles. It is important, as I will explain immediately after. The baton was taken by Alan Bromley. Thank you very much for mentioning it, Professor Angus. And Michael Wright from the Science Museum of London. Alan was at Sydney. And they came, they did again new X-rays. In fact, they started having some tomographies as well, which was very important, not with very high resolution. Unfortunately, Alan died soon after, and Michael Wright visited Australia, visited his house, and he got all the data that he could find. And being a man of very good imagination, he analyzed again and again, and up to now he's probably written about 20 articles, and he has made very good progress on the Antikythera mechanism. So here you see him in front of the Technological Museum of Athens, of Thessaloniki, holding proudly his latest model. This is the front side with some concentric circles. But this here now, he discovered that they were spiral scales, not homocentric circles. And this was important, you will see immediately after. In 2001, we tried to get a permission to do a new investigation of the Antikythera mechanism. The archaeologists were very careful, and we had to have lots of discussions before we actually got a permission in 2005. I think the leading people are Mike Edmonds here with the cap in the middle, Tony Frith, also from Cardiff, these two, Xenophon Moussas and Yannis Bitsakis from Athens, myself from Thessaloniki. Soon after, Mary Zaharopoulou and Eleni Mangu joined the group, and a paleograph, Memos Tselikas from the National Bank of Greece, the Cultural Center, came and joined us. Then after, we had lots of people that helped us and lots of scientists that came up. I would like to mention at least Alexander Jones and John Steele, who have done lots of good work on the Antikythera mechanism. Now, these are the fragments, the four largest fragments, the first A, B, C, D, and these are all the fragments, large or small. Some of the smallest ones, which are about 2 to 3 millimeters, maybe they do not belong to the mechanism, but they have a little bit of sign of greenish turn, and this is why everything is now under investigation. Even crystallographic investigation to see if they all belong to the same mechanism. Names were given to them. When it was discovered that there would have been more than 26 letters of the alphabet, numbers started given to them by Mary Zafiropoulou. For example, fragment 19, which turned out to be very important. With the letters and the numbers that were in there, the Antikythera mechanism was stylistically dated to 150 to 100 BC. So a very old artifact. Immediately we got a permission and we got a grant from the Leverhulme Foundation. We invited Tom Malzbender and Dan Gelb from Palo Alto, Hewlett-Packard, with their fine machine that could investigate the surface features of of the Antikythera mechanism. Here you can see Tom. You can see this. Let me see. Can you see? Sort of. Okay, if you see some white pieces here, these are, I can see them very nicely on my computer. These are little lamps, like a bicycle lamp, not very strong. Each lamp had a computer card behind it, and by pressing a button in a laptop here, the first light comes on, and a photograph is taken by a camera to the fragment. This is fragment A at this time here. And then the second light comes on, another photograph, third light, etc., etc. All 50 lights, they produce a photograph. The fragment is not moved. The camera is not moved. So what is the difference between all these photographs? It's the intensity of the light as they come from further distance or closer, and the direction of the light. And by applying a mathematical algorithm, polynomial texture mapping, Tom was able to actually detect any single small features on the surfaces. Now, this is fragment 19 that I mentioned. Those that are sitting close by, maybe even further out, you can see some letters like Tessera, Lilis, Idomen, some numbers like here. But look how much clearer you can see it with Tom's technique. We can see every single dent on the surface of all the fragments. In fact, I will show you a site. You can enter, you can download all the data, and you can download also the program to analyze them, to have a look at them yourself. You may discover something that you haven't. I mean, there's lots of things that they are still to be discovered on the Antikythera mechanism. Okay, even more important was a high-power X-ray scanner, microfocusing X-ray scanner, that came from Trigg, England. It was about 12 tons that they came, with a very heavy lorry. The largest piece, which was about 8.5 tons, could not be split in smaller parts. You can see it there entering the Archaeological Museum and being set up to start doing a tomography, like a tomography in the hospitals, except that it was much, much stronger. It was, the gun was 450 kilovolts, which means that it could go through 16 centimeters of bronze and stone, as the Antikythera fragments were made of. Okay, let me give you an impression of some of the tomographies. On the left here, you can see fragment D. It looks like a stone, like this. If from outside, you may kick it on the beach, but inside it's a beautiful 63-toothed gear. Now, this is here fragment A, and this is not an animation of data that were made by hand. This is an animation of the data, of the real data that we have. This data exists now in 3 computers in the world. One is in Athens, one is in Thessaloniki, in my office, and the third one is in England. And research is being done on these machines, on these fragments. For example, we do not know what this little feature does. We just do not know. We know what this does, etc., etc. So we have data. We have photographs, normal photographs, like Kostas Xenikaikis photographs, like these ones here. We have the Hewlett-Packard technique, and we have X-rays tomography data like this or this, depending if you put color or not. So we have to solve the puzzle. Now, don't take into account the calculations here. What I only want to show here is that we were able to measure the diameter of every single gear and calculate how many teeth it had. And that was very important. If you want to calculate, if you want to make a weekly calendar, the only thing that you have to do is to take a gear of 365 teeth, measure it with another gear of 7 teeth only, and then when this one rotates by 7 teeth, this one makes a full rotation. If it has a pointer that says Monday, Tuesday, Wednesday, Thursday, etc., etc., you have a weekly calendar. So the ratio, 365 to 7, is what is important to estimate what was the use of this pair of gears. And like this, we have investigated now, and all the knowledge that I will transfer today depends on such calculations and measurements. Let me show you one of the sections of the tomography and one of the mechanics view of the gears. I can put one to one all the gears, and if I continue, I will fill up this picture with red arrows. This was done by Theodora Zacharopoulou, who I really thank you. She's now doing her PhD in our university. Okay, so let's see, first of all, what did the front dials do? The front dials had two concentric rings and at least 3 or maybe 4 pointers. Let me give you here a magnification. You can see much better. So the outside one was divided into 365. It had 365 divisions, the outside one. And it had the names of the 12 months, so it was a calendar, obviously, with the Egyptian names like Phi, etc., all written though with Greek characters. It's like something like the Greeklish of that time. Well, we do communicate with Latin characters quite often, but we really write Greek words. The inside circle was divided by 360 divisions and had the names of the zodiac constellations as we speak them today, like Hydrοχos, Ichthys, Parthenos, Krios, etc. There's only one name, Hyle, which is an ancient name of the constellation of the Gemini. So all the other ones are, as we speak it, in Greek nowadays. Please notice that there is a pin here. Where's my mouse? Here it is. There's a pin there. You can see it there as well. Okay, we do not know what this pin did originally, but now we do know. Let me show you some of the features that I mentioned. Please notice also this little ball here. Let me go one back to show you this. It is here. It can be rotated. Here it shows all white. It was half black, half white. And as the thing was rotating, it could show the surface of the moon, the phase of the moon. So this is here at the moment is almost a quarter or a bit less, maybe 5 days old moon, as is shown here. Okay, so this feature, you can see it was found there. The whole circle here is all around there. This is a crown gear. This is a crown gear that was rotating this phase of the moon. Like this is perpendicular to the rest. And so the little ball, the black and white ball, was rotating around this axis and was showing either the white part or the black part, showing when you have full moon or new moon. And of course, the in-between phases of the moon. Scientific scales I mentioned. So you see, these are part of it, very clearly small. Okay, now let me see. I want to say something more about this outside circle here with Egyptian names of the months. When we investigated a bit more, we found out that it could be detached. And underneath it, there were 365 holes, and the pin could go in one of them. Every 4 years, the user could lift it, rotate it by one hole, put it back in order to calculate leap years. So it was not only a calendar, but it was a very accurate calendar. From your reaction, you can see that you are surprised, but we were more surprised when we started investigating the mechanism. And please wait, there's some even more difficult parts that I don't know how on earth did the mechanic and the scientist manage to find a way of solving such problems. Now let's go on the back dial. I have put here this is the upper part and this is the lower part. So let's first go to the upper back dial. This is beautifully seen in fragment B, A, E, and F that we have investigated. Let me show you the upper back dial. It had, when we measure how many, it has some divisions here that you could see. And when we measure how many divisions there were 235. Now, 235 months is one of the magic numbers that we have in astronomy. Every 235 months, the moon comes on the same constellation and has the same phase. This means that if you know this cycle or period of 235 months, you can predict full moons, new moons, or the phases of the moon, which was very important at that time. They did not have electricity to flip a switch and turn the night into day. Full moon was very important for sailors and farmers. It had also a pointer that is worth investigating. And let me do this immediately after. This is called the Meton's period. So this is one of the X-ray tomographies that we have, one of the sections of the tomography that we have. You see the tip has kind of point here, like a cross, like feature. And now we have investigated the back, but we are just about to write it down. It had a very ingenious way of actually letting the user lift it whenever he wanted and readjust the scales. Let me check this in color. Tony Frith has given me these nice pictures. Especially, I would like to see the very top one here. So let me go 1 millimeter down. And this is how it looks like. It's still there, so the pointer is at least 1 millimeter thick. Let's go another millimeter down, and the pointer is not there anymore. Its width was about a little bit less than 2 millimeters. And there's something, though, at the very tip of the pointer. And in fact, this tip goes in between the spiral sections. And you can see it clearly here. And it seems to enter the gap. So there's a pointer, there's this spiral, and there's a pointer with something going in that, and as the pointer rotates, it follows the spirals. It is forced to follow the spirals. And every time it was going through 1 month, and the next month, and the third month, and so on. Let me look at it in profile. Well, it is a tip, it is a pin that goes between the scales, and it reminds us very much a modern, well, semi-modern nowadays, tip of the record players that we used to have playing vinyl records. The same principle. Okay, this is what it looked like. Now we have investigated the back of it. The work was done by Lina Anastasiou, but also Kyriakos and other students have helped on this. So this was moving like this here among in the scales, showing every time where the month, which month we are, and so with this they could predict, for example, full moons. Okay, let me go now to the. So the upper dial had 230 divisions, which represents the Metonic cycle. It had also somewhere here, it had a 4-division dial that originally we did not know what it was, but later we discovered it, and I will tell you about it soon. I remind you, 235 months is about 19 years. This is when, in 19 years, the phase of the moon comes exactly the same place in the sky and has the same phase, which means that if you reconcile the rotation of the Earth around the Sun, the solar calendar, with a lunar calendar, which is a rotation of the moon around the Earth. So this was discovered by Meto of Athens. Okay, let's go now to the bottom back dial, which was a spiral. And when we investigated it, we found that it had 223 divisions. And again, this is a well-known period, a very important period for eclipse hunters like myself. Every 223 months, the eclipse pattern repeats exactly the same way. For example, if we had an eclipse 3 months ago, or if we have one, let's make it simple. If we have an eclipse today, a solar eclipse, and after 15 days we have a lunar eclipse, and after 6 months we have another lunar eclipse, and after 10 days we have a solar eclipse. After 223 months, we're going to have the same pattern. A lunar eclipse, 15 days a solar eclipse, 6 months later a lunar eclipse, 10 days later a solar eclipse. Once you knew the cycle, you can predict eclipses. And we know, at least Herodotus mentions that Thales of Miletus much earlier had predicted the solar eclipse I must say, as an astronomer, I cannot believe that he could predict the location of the eclipse, but he could predict that an eclipse will take place. So just before a battle between two kingdoms, between the Lydians and the Persians, he told them, well, look, the good God is very, very sad that you are going to have a fight, and he will take the sun out of the sky if you continue. Well, this happened, and it prevented a battle between the two kingdoms. I mean, this is one of the stories of Herodotus, which is a historian, of course, of the ancient times. Okay, now 223 months is about 18 years, and it was found again in the Antikythera Mechanism. I will show you a little bit more about it very soon. Okay, let's study this lower back dial a little bit more, mainly fragment A, fragment F, and fragment E. These are the ones that it looks again like a stone. Please don't kick a stone that has a little bit of green on the beach, because it may have something important. Let's do some tomography. Immediately inside, you can see some of the spirals. If you look carefully, you see some letters on it. And let me show you a magnification of this. I think as you can see clearly some kind of glyphs. We call them glyphs between the British colleagues and ourselves because we do not know what they meant. Engraved symbols. Now, it took us some time to find out what they were. Let me paint them so that you can see them easier. You can see always there's an eta, an anchor-like feature, some numbers. This could be the number 6. A iota is here. A sigma again. The anchor is always prominent everywhere. A mi eta here. A sigma, eta, I cannot see very well up there. There's an anchor here again, and again, the eta again, sigma. What do all this means? Well, it occurred to us that if it was to predict eclipses, because it was on the 223 division circle, it had to do something with the sun and the moon. So, eta, oops, sorry, what happened? Have I put it? So eta was mentioned, it was for the sun, Ilios. Sigma was for Selene, the moon. This was for the month, and this was not an anchored symbol. It was the first two letters of the word ora, omega rho, which means time. So when the pointer was reaching one of the divisions that had such characters, such engraved symbols, it would warn the user that at this particular month, at this particular day, at this particular hour, you're going to have a solar or a lunar eclipse. I mean, it is something really, really difficult. Okay, let me have a look also at this on fragment A, at the back side of fragment A. This is, okay, you can really see what I mean by divisions. It's very easy to see them there. There are some places where glyphs or engraved symbols were made. This is a Hewlett-Packard technique. You can see it so clearly. This is most likely the letter theta, which is the number 9 in ancient Greece. So Selene, ora, 9. So 9 o'clock could be something, maybe an eclipse. So I will go on here. We have found 18 of them by now. There are 16, the location of 16 of them are mentioned here. And if you put them all in a row, again, Tony did this work. Let me clean them. You can see again all the sigma, etc., etc. And now this is what we have. Sigma for the sun, for the Selene, eta for Ilios, Helios, ora, hour, the day, and a numerical value. So this is a machine that could predict eclipses. So the lower back dial was for the prediction of eclipses with its pointers. Now, we had to find somewhere there a gear with 223 teeth. It was always there, but no one had paid attention because it was moving so slowly. But of course, it was 223 months. It was moving slowly. People had ignored it or had said, maybe it is for artistic reasons. It was not. It was a real calculating gear. Nearby, there were two gears that drew our attention, and I would like to stay on them a little bit, and I think this will be the last thing that I'm going to describe in the mechanism, an ingenious device. So let me see them a bit better. It has here a dent. It was identified by Pericles Radiadis in 1903. He called it endomy, so cutting. Let me see it a little bit better with the tomography. It is there. Now let me go one down. There it is the endomy. I go back, down, up, down, up. You can see it is always 50 gears. It's not one gear. There are two gears on top of each other. One of them had a slot, and what did the other have? It took us some time with high-resolution tomography to find what the other thing was doing. So let's look at the high-resolution section. You can see that the endomy, the cutting, goes all the way here, and it is blocked somehow here. So there is a pin from the bottom gear engaged with a slot of the upper gear. And as the bottom gear rotates, it rotates the upper gear as well. But again, this is illogical. Two gears, the same number of teeth. Why should they build them like this? Until we found that the axes of the two gears, they were not coaxial. They were displaced by 1.1 millimeters. So the pin was engaged either close to the periphery, close to the circumference, or closer to the center of the gear, rotating it faster or slower. And that was really something that we couldn't believe when we calculated how fast and how slow it goes, because it follows the movement of the moon on the sky. The moon rotates around the Earth, the orbit of the moon around the Earth is not a circle, it's elliptical, and goes closer to the Earth in the perigee, going faster, and away from the Earth goes slower. And the mechanism with this ingenious device was doing exactly these calculations. This is in the bottom here. You can see what I mean by displacement of the axis by 1.1 millimeter. So this is how the pin was rotating faster and slower in the top gear. Now, for the astronomers, of course, we all know that this is Kepler's second law. So Kepler's second law was known at the time. In fact, when he searched Ptolemy, he mentioned that this was called the first lunar anomaly of Hipparchus. So it had another name. Now we teach it to our students as Kepler's second law. But they not only knew it, but they had actually used it. Okay, now this is something, very recent research. Maybe the Antikythera mechanism, as it has a very difficult motion of the moon, probably had also the motion of the sun, which also goes faster and slower, faster and slower. This you can see in sundials, that they always have a correcting plate by the sundials. So there are two ways, according to James Evans from Puget Sound in the United States. Instead of having this time the pointer moving irregularly, he said that it could be that they had the scales, the division of the scales were irregularly inscribed. And there are two methods of doing this, either with an eccentric circle or with a thing like this, as I have mentioned here. So this is some recent work of Jim, with whom I collaborate now on something else, on the parapigma of the Antikythera mechanism. This is a full scale of all the gears, seeing them in profile. You see here on the right, it is the eclipse prediction train of gears. This is the Metonic circle. And here I have put something about Olympic games. Let me see what I mean there. But before doing this, I would like to show you that the upper back dial had 19 times the 12 months of the Greek calendar. The Greek calendar, which Greek calendar? Every city in ancient Greece had its own calendar. So it was easy for us to go through the book of Trumpi, a German PhD, who had actually catalogued started with a PhD and then a full research, every calendar of every ancient Greek city. And we found, much to our surprise, that it had nothing to do with Athens, and even more surprisingly, it didn't have anything to do with Rhodes, because we thought that it was probably done in Rhodes. Also, with this calendar now that we know that this is the Phoenicians with the first month and this is the last. Originally, we did not know if the scales start from here going that direction or if it starts from the inside and going the other direction. This is the names of the months that we have found. When we checked the calendars, this is the Antikythera Mechanism calendar, all in red. And this is the coincidences with the calendars of Corfu, Kerkyra, of Dodona. There's only one month which is different. And the Vuthrotos, which is in southern Albania, just above the border of Greece, north of the border of Greece. And when there's also one city, the Tapromenion in Sicily, that has also many similarities. But as you see here, Athens, Rhodes, etc., there were absolutely no coincidence. All these are Corinthian colonies. Unfortunately, we do not know the Corinthian calendar accurately yet, but Professor Kritzas is working on it, and he may find something later. Now, these are the names of the month. And now let me show you these cities that I mentioned. They're all in northwestern Greece or in Tapromenion in Sicily. Rhodes is in this part of Greece. The Antikythera Mechanism had also a series of astronomical phenomena that occur once a year, and their sequence depends on the geographical latitude. So if you observe this phenomena from, say, Alexandria, it could be different than from England. So we try to find if the sequence of the Antikythera Mechanism astronomical events coincided with what geographical latitude, and we found that we find this graph, it has a certain minimum. We have many, many tries with different calendars, and it looks as though it goes between 33.3 and 37 degrees north. Now let me talk to you and finalizing for the Meton cycle and the crown games found in there. So this is a very high resolution X-ray tomography inside the upper circle of the Metonic circle. And you can see some letters here, but now let me outline them. The first thing to notice is this word Nemea, but we thought it is Nemea, a city close to Kerkyra. This could be Nemea, which are one of the crown games in ancient Greece. Oh, then we found the letters year, this means year 1, year 2, year 3, year 4. And we knew that the Nemea were taking year 4 and year 2. In fact, we did find some of the letters the other side, again from Nemea. And of course, we had to search for Olympia in the first year, and we did find it. And then the same year, and every 2 years, were the Isthmia. We found this as well. The Pythian games that were done in Delphi were every 4 years, and they were again where they should be on the third year after the Olympics. And we find much of a surprise also the Naya or Na, which are done in Dodona. Again, indications of use of the machine in northwestern Greece, as with the calendars. The Antikythera Mechanism, as I said, it was a complicated machine. It had 2 doors that were covering the plates, and we have found on them a very large number of letters, words. This is an example of this, with some astronomical Aphrodite, astronomical terms marked, like Helios. This styrigmos is when Venus is a very bright star. It's not a star, it's a planet next to the sun, and on the 6th of June, it goes in front of the face of the sun. If you can buy some of these solar glasses, look at it early in the morning until about 1 o'clock. Look at the sun, you see a dark spot going through it very, very slowly. Within 6.5 hours, it goes through the solar disk. And this is a very rare phenomenon. The next one, if you do not see it this time, the next one, no one in this audience, I think, will be able to see it, because it happens at 2117. So a long, long time from now. The Venus reaches a maximum elongation away from the sun, and then goes the other side of the sun, reaching the same elongation, 47 degrees. The point of turning is called styrigmos in ancient Greek. And you have found the word styrigmos quite often. This is a small statistics for this. We have found astronomical, geographical, and technical terms, how to use it, how to put the axis on the plates, etc., etc. In the university, Lina Anastasiou and myself, her husband, has made a new true type font. We call it the Antikythera true type font. I have written this with this font, copying the letters on the Antikythera mechanism. For those that cannot speak Greek, what I have written here is who constructed the Antikythera mechanism. These are all the letters that we have found. In fact, quite often I communicate with my student with the Antikythera font. It's fun. And I have used Photoshop to write exactly what is on fragment 19 that I showed earlier, very clearly with this font. Please notice that this I didn't mention before, it was not very obvious. Iota theta, this is 19 years, the year I have mentioned already. This is 76 Omicron, and 6 is this sign is for the 6. This is 76, the Callippic year, which is 4 times the Metonic cycle. Sigma Kappa Gamma is 223. This is the Saros cycle. So you see what I explained to you is it. Another thing to investigate is what these spirals. Are they Archimedean spirals? Archimedean spiral is a spiral that as the angle rotates, the radius increases. So it goes like this, increases, 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 comes around and goes through it again, and still increasing. This is the Archimedean spiral. But it is possible to make a spiral with what we call the two-circle spiral. So you start with a hemisphere, a semicircle, with one with longer, larger radius, and so on and so on. This looks also a perfect spiral. I wish we had found this was an Archimedean spiral. We haven't. It is the person that actually did the spirals did it the easy way with semicircles. So this was not so what we had expected. But maybe Archimedes is still, maybe he was the grandfather of the mechanism. This is a mechanical flow diagram of all the gears and what they do. I would like to show you some of the very difficult axles and shafts that the mechanism had. I mean, this is the most difficult part to make, not so the gears, but the axles. Sometimes they start, first of all, some of them are double. They start sometimes with square base, it comes round, and then again square. So it was very carefully made to work with the gears. This was done by Kyriakos Evstathiou. This is one of the trains with a pin and slot mechanism. You can see it here, rotating. Let me see why it doesn't do it. There it is. This is the pin and slot mechanism. I will go on because I know I'm a bit late in my timing. These are all the gears that we cut because we decided we can make a model from now on. The largest and smallest are shown here. This has 224 teeth. There's another one as I have mentioned, which is had 223. And the smallest one, with a diameter of less than a centimeter, has only 12 teeth. To see them there in the hand of Kyriakos Evstathiou, or to compare their sizes here. We decided to continue building our model. It took us a long time. We tried again and again, nights and days before we managed actually to make the mechanism, the model that we have. We threw many plates, many gears, many axles. We made lots of mistakes. But this is our first model, which looks, I think, very nice. This is now at the Observatory of Thessaloniki. And now we have a second model that we have donated to the Archaeological Museum of Athens. And we have decided to cut a slot here that people can see the gears inside. And of course, it has the newest research as well. Articles were published, for example, front cover at Nature, or another paper in Nature, other in the History of Astronomy, and other journals, mechanicals, etc., etc. The university has given us a grant for the Antikythera mechanism. We have a very nice committee with an archaeologist, a mechanical engineer, and the astronomer. And we have found a gifted student who has her first degree in archaeology and history, second degree in physics, and third degree an MSc in computational physics. Lina Anastasiou was born for the Antikythera Mechanism, and she has done a very, very good job. I would like to thank you very much. This is the full team. I leave a few questions, some of which I have answered. This is the page of the Antikythera Mechanism, where you can have links, videos, etc., etc. It is very easy to remember, I think. Well, thank you very much. This is my end. I appreciate you.